Stargazers and cosmologists have forever been captivated by the universe due to its huge assortment of star systems and other heavenly wonders. Yet, a new revelation has stunned cosmologists. They assume they grasp the universe's origins and how it has changed over time very well, but there is an error between two estimates of how rapidly the universe is expanding at present. This might be the first sign that they must fundamentally change their understanding of the universe. You may have heard about the crisis in cosmology. The main reason for this cosmological crisis is that different methods for determining the age of the universe are yielding varying results, and cosmologists do not know why. The situation has worsened recently due to new research conducted with the James Webb Space Telescope. The glaring inconsistency remains even after Webb refined previous estimates of the expansion rate using data from the Hubble Space Telescope. The expansion rate of the universe is measured by the Hubble constant, named after astronomer Edwin Hubble. Cosmologists determine the age of the universe with the help of this rate of expansion. The difference in the values of this constant, calculated using the most advanced techniques available to cosmologists, has led to the current crisis in cosmology. In fact, this discrepancy suggests that the universe's age could vary by about 1 billion years. The first and more indirect method used was studying the cosmic microwave background radiation, CMBR. Space is filled with the remnants of the Big Bang's electromagnetic radiation, or the CMBR. To estimate the universe's age, cosmologists examined an imprint of the early universe from a time shortly after the Big Bang and compared it to a current model. Using this method, the calculated value for the Hubble constant suggests an estimated age of 13.8 billion years. The second method takes a more direct approach by studying variable stars, such as Cepheids. These stars exhibit fluctuations that can be used to determine distances to nearby galaxies and, ultimately, to galaxies farther away, creating a sort of distance ladder. For more distant galaxies, cosmologists use type Ia supernovae. By comparing the intrinsic brightness of these supernovae to their observed brightness, researchers can calculate their distances. Using this method, the calculated Hubble constant suggests an estimated universe age of 14.5 billion years. The Hubble constant refers to the rate of expansion of the universe, but the disparity between the results of the two methods is known as the Hubble tension. This is the heart of the crisis in cosmology. But this crisis deepens further. Despite advances in astronomical research, one fundamental question remains. How is matter distributed in the universe today? This question arises from the conflicting findings of numerous cosmic observations. Cosmologists and scientists have struggled to reconcile their differing perspectives on the current distribution of matter, giving rise to the unexplained S8 tension, a measure of the lumpiness or distribution of matter. Bunching in the universe. The construction of the faraway early-stage universe can be unequivocally assessed by low redshift information, including frail gravitational lensing studies. Still, the qualities got from low redshift perceptions disagree with the worth of S8 determined from the Standard Model of Cosmology, which depends on estimations of the vast microwave foundation. The S8 strain emerges from this error. There is clearly something that challenges our comprehension, declining to agree with many hypotheses, perceptions, and the speculative substances that support those hypotheses. Stargazers utilized one of the most powerful supercomputers on Earth to run the greatest cosmological reenactments yet to tackle this puzzle. The Full Hydro Huge Scope Design or Flamingo project at Durham College in the United Kingdom is a supercomputer with 30,000 processors. This task's extent becomes obvious when one realizes that the recreation required over 50 million hours of computing time. The goal of these reproductions was to offer a thorough arrangement. Unlike earlier recreations that solely considered how dark matter would influence the universe's development, the effects of dark energy, the unexplained energy source driving the universe's accelerated expansion, are also included in Flamingo. To test their speculations, cosmologists use recreations like Flamingo, where they adjust the boundaries to find which combinations result in universes that reflect our ongoing comprehension of the universe. The Flamingo reenactments open a new virtual window on the universe that will help capitalize on cosmological perceptions. Moreover, the enormous amount of virtual information presents opportunities for testing new methods for data analysis, such as artificial intelligence, and for making new theoretical discoveries. Cosmologists can then predict random virtual universes using AI. They measure the values of vast boundaries by comparing these with large-scale structure perceptions. Additionally, by contrasting data that limits the impact of cosmic winds, they can calculate relevant uncertainties. The most complex flamingo recreation is significantly larger, occurring in a region of space covering over 9 billion light-years on a side and filled with 300 billion particles, each the size of a small galaxy. Yet Flamingo is unique in more ways than just the scale of its reenactments. It also considers the effects of normal and dark matter. Many prior recreations, such as the Millennium Simulation, focused on dark matter, the invisible material that makes up around 85% of all matter in the universe. Scholars suggest that cold dark matter hardly interacts and thus can be modeled solely by gravity, making it computationally convenient. However, it turns out that normal matter cannot be ignored, even though it constitutes only 15% of the universe's material. For instance, the very massive black holes at the centers of galaxies generate magnetic fields that drive matter back out into space as they feed on normal matter. The intergalactic material that these winds collide with influences the formation of new galaxies. This means cosmologists must incorporate fluid dynamics, a branch of physics that demands significant computing power, into their reenactments. Flamingo is the largest project to do this. However, even this expansive approach, which accounted for extreme processes, failed to explain the weak clustering of matter observed in the present-day universe. Professor Jup Shea of Leiden University expressed his bewilderment, stating, "Here I am confused." While the recreation was a significant step forward, it did not provide a definitive solution to the S8 pressure. Cosmologists remain unsure about the origin of this strain, leaving room for various intriguing possibilities. The team hypothesizes that the conventional model of cosmology, or even the standard model of physics, may have flaws or that the effects of normal matter might be more significant than previously believed. They suggest that dark matter may possess unusual self-interacting properties not found in the standard model, potentially indicating a breakdown in our understanding of gravity on the largest scales. Although the Flamingo project could not resolve the S8 strain, it provided insights into the complexities of matter distribution in the universe. These results offer cosmologists valuable new information and may highlight errors in existing data, helping to address the mystery of this baffling cosmic phenomenon. As they search for solutions, astrophysicists and cosmologists are considering the possibilities of new physics and a revision of the standard model. The enigmatic S8 pressure serves as a reminder that there is still much to learn about the universe. As we continue to explore its mysteries, it also presents opportunities for groundbreaking discoveries and advancements in our understanding of the cosmos. With powerful telescopes like NASA's James Webb Space Telescope, which recently collected data that confirms and expands on the Hubble tension, cosmologists will need observatories like James Webb and highly detailed simulations like Flamingo working together to resolve these conflicts in the standard cosmological model or perhaps develop a new one. What do you think? Share your thoughts in the comments section. Also, if you are new here, don't forget to subscribe to our feed for more fascinating space-related content. Thanks for reading.